Thanks for having me. I'm going to talk about two works. First one is on my own. The other one is with Lucas. He's in the audience. I'm going to talk about magic states. Okay. So, to probably do something useful with a quantum computer, probably fault tolerance is necessary. And the good news is that we have this threshold theorem, which says that if the physical error rate is below the threshold, then we can just scale up the system size and make the error rate arbitrarily low. I usually always have this, and I'm glad to see Dorit here, actually. I had this before I knew you were coming. FYI, yeah. Okay, so it's good to think about that's good, but realistically, it's good to think about what kind of quantum computer we want to build in the far future. And last year, there was this interesting program from DARPA called Quantum Benchmark Initiative. And in one of the documents, they had this pretty interesting plot. So they basically surveyed a bunch of quantum algorithms that they are interested in. And they basically plotted the number of logical qubits that you need and the number of the gates that you need. This is the number of T gates, by the way. It doesn't include a Clifford. And I do think this is a bit of an overestimation, but just as a broad stroke comment, you can see that there are some indeed problems that they would like to solve using a somewhat large, but not crazy quantum computer, 100 to 1,000 logical qubit type of thing. But you can see that a lot of things have a gate count that is actually quite large. Let's say almost around the order of 10 to the 12, 10 to the 14. As I said, I do think this is an overestimation, but it's important to note that if we just take this as a face value, the common way in which people think about the total computation time for the fault-tolerant quantum computer is basically the number of T-gate count times the time to execute that T-gate, at least for now. And if we just plug in these numbers, and if we put in a pretty optimistic estimate for the time to execute T-gate, let's say 1 microsecond, which is super aggressive, then we get a number which is around the order of years. And obviously, probably we're not going to exactly use this framework to solve exactly those kind of problems, but it suggests that this way of thinking might run into some issues if you want to run algorithms in this part of the plot. Okay, so it's interesting to think about where all this way to estimate the total time came from. I would say there are many people who already argued that the cost of the T-gates is significantly more expensive than the cost of Cliffords, even before this work. But this work encapsulated very nicely on why this is a reasonable approach under some architecture. And the point is that any quantum algorithm can be broken down into a sequence of unitary operations of this form, or P's of Pauli. And each of those operations can be realized by consuming a single magic state like this and doing some a simple lattice surgery operation, say on a surface code. Okay. And back in 2019, this kind of assumption was kind of reasonable, because if you look at the ways in which people envisioned creating magic states, say on the surface code-based architecture, you would see these pretty clever, but still very horrendously large diagrams for creating one or a few magic states. So there is a definite consensus that the cost of the magic state is much larger than the cost of Cliffords, at least back then. But in the meantime, I would say last year, there's been some pretty developments in pretty hacky ways of creating magic states, and I'm going to tell you more about that. And I wouldn't say we're quite at the level that the cost of a magic state is really comparable to a Clifford. I think it's still more expensive, but we're at a point where there are these various hacks that we can apply, and it's not totally clear whether the magic is significantly more expensive than Clifford. It's just kind of a very murky period, I would say. Okay, so I do think that more progress is going to come. And in fact, if you look at the archive yesterday, there are 2 papers, which is basically in the same spirit. So progress is happening. And in the far future, if we have a quantum computer that can create lots of magic, it's interesting to think about and if we optimize for time, what is really the best thing we can do, just to have some a base point. And there was a very nice work by Austin Fowler who answered this question already in 2012. And he showed that basically by creating a bunch of resource states in parallel, so if you have unlimited qubits, you can just do like a logical gate teleportation like super fast. And once you do that, in principle, for a very large computation, the total computation time can be brought down to the measurement time at the physical level times the t-depth of the circuit. If you don't know what t-depth is, I'm going to define it shortly. So obviously, you'll almost never use this because like this uses like a ginormous amount of qubits. That said, it really gives you like a good baseline on how fast you can like push the speed of the quantum computation if you want to. So probably the something that we're going to arrive to solve some of these like super challenging problems by DARPA will be somewhere in between these two. So we probably won't apply these T-gates in a sequential way, but at the same time we won't have these like enormous number of qubits. And I'm not sure like what exactly will lie in between the two. This is a big problem actually. But today what I want to tell you about are the questions that are motivated about this bigger open problem. So to that end, I will tell you about two things. One is about like if you really want to push for the parallelization of the quantum computation, like how far can you push it? And secondly, I'll tell you about some recent progress on making the magic state cheaper. Okay, so first of all, t-depth. If you don't know what that thing is, suppose we have a circuit which consisting of Clifford and T. And you organize your circuit in such a way that you have like commuting layers of T's, and then you have like a Clifford, and you have this in an alternating fashion. And what you see here is basically a circuit whose t-depth is 2. And you can imagine like optimizing over this like all over possible combinations of Clifford and T circuit. And the minimization, the minimum number is the t-depth of the unitary. Okay. As I said before, in principle, using this time optimal method, the computation time can be brought down to the physical measurement times the t-depth. Okay. And what I'd like to tell you today is that actually there's a sense in which time optimal method is not truly time optimal. So what do I mean by that? So imagine in the far future, you have like a super large scale fault-tolerant quantum computer in some server farm, and some engineer turns on a quantum computer, and it's like ready to like service for your customers. Okay. And maybe the first person like factors some large integer, and then the next person comes along and factors another integer, and this thing just keeps going, okay? All right. Okay, so a fun fact is that if you really optimize for time, and if you want to factor n-bit integer, so the circuit depth can be brought down to like a order log n, okay? So this is like known like very well, but like it's not like written down super explicitly. If you're curious, I can tell you about later. Okay. And just to grab your attention, I'm going to tell you about if I'm going to tell you that there's a slightly different way of running these applications that can change this picture. So the keyword here is catalytic quantum computation. It's an approach that has been known for a long time, but it was very strongly advocated by this math paper in 2023. And the one way to think about this is this. So, when you turn on your computer, like a normal computer, you don't like immediately toggle bits. Like it's not like you turn on your computer and apply like AND gates and things like that. There's some things that are loading in your computer, right? So like you load your operating system on the RAM, for example. Okay? So you can imagine doing something similar to a quantum computer too. So you turn it on, and you're going to create some states that will be useful for various purposes. So there'll be some like time in the beginning that you use to prepare some special states, which will be your resource. And then you can imagine running the same types of applications. Okay? And just to grab your attention, what I like to claim is that this can be brought down to a constant. It's like if it's like an n-bit factoring, I think. I haven't thought about like optimizing for time, but like n cube. Yeah. But it's a one-time cost.
So it's n cubes, and then are you polynomial computation?
Yeah, you can just do this forever. Yeah.
You don't consume these catalysts.
You do not consume. That's right. Okay. And that's a great question because that was exactly what I was going to say. So what do we really mean by a catalyst formally? So the goal is that you want to apply some unitary many times. This could be some simple things like a single qubit rotation, or it could be like addition, multiplication, maybe sorting, or it could be something more complicated like factoring. And so what you want is you're hoping that there's some special state called psi c, let's say, such that if you apply a different unitary u prime, you end up getting this u while keeping this psi c intact. And of course, if u prime is more expensive than u, there's absolutely no point in doing this. But the surprising bit is that in many cases, you can find the psi c such that u prime is actually cheaper in some sense. So this is kind of like a bread and butter of like a fault-tolerant quantum compilation. A lot of work has been done in this direction. But these were all used to basically get like a constant factor improvements. And the new development is that having a catalyst seems to give you like a actually asymptotic difference in the circuit depths. So here's a list of subroutines that you can apply in constant t depths, like a single qubit rotation, like addition, multiplication, quantum Fourier transform, and quantum part of Shor's algorithm. And there's also a recent work on random geometries. Yes?
What is rotation?
Single qubit rotation. Yeah, thanks. Okay, so that's quite a lot. So how do we really understand this? It turns out that there's a simple way of understanding this, because there is a nice work, which is due to, it's really a combination of two works. One is due to Hoyer and Spalick, and the other is by Takahashi and Tani. And their result together implies that if you have like arbitrary, like a 1 qubit gate with unbounded fan out just means like a copying information classically, right? So, and you can see that this can be realized by like a sequence of C0 gates. So this is just a Clifford. So if you have this operation and a 1 qubit gate, arbitrary 1 qubit gate, then you can do all sorts of crazy things in constant depths, like sorting, arithmetic operations, quantum Fourier transform, et cetera, et cetera. Okay, so insofar as, well, obviously this doesn't consume any like T gates, so the only source of magic is like really here. And the key claim is that arbitrary, like single qubit unitary can be done in constant T depths. That's really the main claim. Okay, so of course we can reduce this problem further because like arbitrary single qubit rotation is really a composition of like a 3 rotation in 3 different axes, each of which can be converted by some Clifford. So if you can do like a arbitrary rotation in like one axis, like let's say Z axis, then we're basically done. Okay. So this is a extremely well-studied subject, needless to say, because it's like one of the things that we're going to have to build when we build a large-scale quantum computer. So for one thing, as a starter, everybody, like if you learn quantum computing, one of the first things that you learn is that there's a Solovecki-Tayev theorem, which says that using a discrete gate set, you can synthesize arbitrary continuous gate set for like a reasonable discrete gate set. And for the Clifford plus D, if you don't use any ancilla, essentially the optimal answer is no, by this very nice paper by Ross and Selinger. And if you use some ancillas and some like a catalyst states, you can actually do slightly better for like a small values of alpha. But all these methods, they're kind of sequential in nature. So it's like you apply T-gate, you apply Hadamard, you apply T-gate and Hadamard, T-inverse, yada yada. So by construction, the depth of all these things are at least like a log or 1/epsilon, where epsilon is the target approximation error. So how do we get around this problem? The main idea is the following. So, so just to make sure that I put this very clearly, there will be 2 ideas in the main idea. Okay, so this is the high level, and in the next slide, I'm going to tell you about why these things are important. So hypothetically, suppose you have some Clifford. I'm going to call it as U, and it has some special properties. First of all, it is a constant depth circuit, Clifford. Okay? And at the same time, it has a large period. Okay, it's a n qubit Clifford, and its period is like exponentially large in n. Then there must be some eigenstate of U such that it has an eigenphase which is proportional to some constant divided by, n, basically. So somehow, if you can, my claim is that somehow if you can find something like this, then you can, apply this phase very efficiently. And the approach is basically prepare a random eigenstate using quantum phase estimation and use the phase kickback trick to apply the rotation. I'll be more specific. So why are these conditions important? So why does the U being Clifford help us? When you prepare a random eigenstate, well, maybe there are other methods, but the easiest thing to think about is to do the quantum phase estimation. And this is the standard quantum phase estimation circuit. And each of these U's, this U, if it's a Clifford, then the square is a Clifford. Like, in fact, like if you raise U to the 2 to the T power, that's still a Clifford. And in fact, you can just compute it very efficiently by this repeated squaring. Okay? So that makes our life easier. If U was some like arbitrary low depth circuit thing, this would not have worked. And secondly, if U is low depth, then the control U can be also made low depth if you include like more ancillas. So what you can imagine doing is that if you have an eigenphase of e to the I theta, you just apply the control unitary. So it will apply unitary only if this guy is 1, and if it's 0, it doesn't do anything. And that will do this like a standard phase kickback trick. So that's the rough idea. The only question is, how do you find such a unitary? And honestly, I asked ChatGPT, and it actually gave me an answer. It's a true story, actually. Yes. Yeah. So yeah, it told me about. Well, it didn't really tell me about this specific thing, so I had to like decode what he was saying. But
Can you say exactly what's the claim that you're trying to prove?
the claim is that there's an n-qubit catalytic state, so that any arbitrary single qubit rotation can be realized in constant t depths. And it's basically idea is to use a finite field, GF2 to the n. And I won't go into all the details, but the point is it gives rise to a very natural matrix, like a binary matrix, that can be interpreted as a Clifford. And it has a desired property that its period is actually exponentially large in n. And if you kind of stare at it, the left part is actually cyclic permutation of the bits. So there's an easy way to do that in constant depths if you have some ancillas. And then you have this other thing, and the claim is that both of them can be actually realized in constant depths. So the first one, cyclic shift, in case it wasn't obvious, like let's say these are the qubits that you want to apply the cyclic shift to. Then you can just prepare these guys in the all zero state and do this like a depth 2 like swap circuit, and it just moves everything in one direction. For this one, this is basically doing a control knot from 1 qubit to a set of qubits. So if that set of qubits is large, then we can't actually guarantee this is low depths. There's some very technical reason why this is actually okay, no matter how large this set is. But just for the purpose of this talk, just bear with me that, and let's have a practical mindset. And I can assure you that when n is less or equal to 660, people have enumerated this mathematical object on some website. And let's see, the size of this set is at most 4. Okay, so let's just say for all intents and purposes, this is just some like a constant size circuit. So at the end of the day, what we have, so we have a Clifford, okay, which applied to some state corresponding to bit string, applies some like invertible binary matrix, which is a Clifford. And we can write down all its eigenstates. And it basically looks like this. You have like 2 types of eigenstates. Because we're applying a binary matrix to a bit string, there's this like a trivial eigenstate, which is an all 0 bit string. It just doesn't change. And there's a other one which is kind of like a quantum Fourier state, except over here we don't really have the standard bit strings, but some like encoded version of this bit strings. And the important thing is that you have this like a nice distribution of the eigenphases over the unit circle, which is like almost uniform. So there's like a single point with like a double multiplicity, which is the eigenphase corresponding to 1. All the other points have just exactly one eigenphase. Okay, so let's recall that if UF has constant depths, then the control version can be made constant depths. And because UF is Clifford, you can estimate this phase efficiently. Okay? And therefore, there is a constant T depth catalytic Z rotation, which means that insofar as you can create a state like this, and just trust me, you can do this in polynomial of time in n, then you can apply arbitrary rotation in constant T depths. Fun fact, after I put this paper out in arXiv, Craig got really into like optimizing this circuit. So initially, my construction had a T depth of 3, and the size of the catalyst state was n squared. And then Craig just came up with something that is a little bit different. In many ways, it's better. And he had a T depth of 2 and a catalyst state of n. Now it's getting like pretty practical. And then a few days after, he told me again, and he said, oh, actually, if you apply like many rotations like sequentially, like side by side, some of these gates cancel each other out. So in that limit, the T depth becomes basically 1 plus epsilon, where epsilon is the number of gates that you, 1 over the number of gates that you apply in sequence. And the catalyst size remains n. So what's a little funny is that it's proven that this stupid single qubit unitary has a T depth of 2, actually. So in some sense, rotation has a T depth which is strictly lower than this very simple looking thing. Okay, so the key takeaways is that it seems like catalysts can let us do things that are seemingly impossible. At least to me, it wasn't obvious that you could apply like arbitrary single qubit rotations in constant T depths. And not to mention that there are these various other things that you can do, like integer arithmetics, quantum partial algorithm. And this seems to be very surprising to me. And of course, one might say, oh, this is just like a log factor. But remember that these are the kind of subroutines that you like use over and over in like various quantum algorithms. So I think this could actually lead to like pretty meaningful speed up. Good. So yeah, and of course, right. And this is now the point at which I segue to the other part of the talk. And it's, this is all very nice, but ultimately, these things will become meaningful only if we can apply like many T gates at the same time, meaning that when the magic state is very cheap. So I'm going to talk about some recent progress on this. So conventionally, how do we really think of a magic state? We were like for a long time kind of focused on this like a surface code based model of quantum computation. So we thought we have these like cheap Cliffords, and you would inject a noisy magic state and do some magic state distillation. There's been some like ongoing recent progress on creating magic state using some small code and somehow growing that small code into a larger code. So this idea really actually goes back to the work of Goto in 2016. So it's actually pretty old, but recently there's been some like improvement in the actual implementation, which reported numbers that seem actually pretty good. So just to make sure that we're on the same page, there's this textbook method for injecting a magic state, right? So say you have a surface code or a toric code, then you prepare 1 qubit in the magic state that you want to prepare other qubits either in the 0 or plus state, and then you measure the syndromes and apply some correction, and then you get an encoded magic state. And the error rate of the encoded magic state, because it was coming from a noisy physical magic state, it has an error rate of order p, where p is the physical error rate. So for a long time, people thought that this is like pretty much, there's no way around this. But there was like a nice paper by Ing Lee in 2015 who showed that actually if you use error detection, like without using any like extra code, just by doing error detection while you're doing this, you can actually get a magic state whose error rate is like a less than p, which is like p over 2 actually. And there's also some nice work from PsiQuantum which like expanded on this method. So this is one of the early indications that by doing post-selection in some way, you might be able to actually improve things a little bit. Yeah, I'm going to tell you about like one of the ideas that could make such an improvement. And this is an idea which is based on it's really an old idea, which has used a transversal non-Clifford gate. So where this idea is coming from is based on the following. So ideally, because like non-Clifford gates are expensive, what we'd like to have is some code that has like a high threshold, so we can actually do error correction using the hardware that we're going to build, and it's compatible with the and it also has like a simple fault-tolerant non-Clifford gate, say some transversal gate. However, empirically speaking, codes with transversal non-Clifford gates tend to seem to have like a lower threshold than the ones that don't. I'm not sure if we have like a no-go theorem for this, but the fact of the matter is like we just don't have such a code. It seems really hard to get a code that satisfies all these criteria. So the idea behind our work is actually quite simple. So it's very easy to find the following pair of codes. There's code 1, which has transversal non-Clifford gate, but it has a bad threshold. And you have code 2, which does not have a non-Clifford gate, but it has a higher threshold. Like think about like a 2D toric code, for example. And somehow the hope is that you combine the best of both worlds. So somehow you want to keep this transversal non-Clifford gate part while somehow keeping this like a high threshold. And the idea kind of sounds really dumb, but it actually works. And the idea is that you just create the magic state using code 1, and instead of doing the like a whole full error correction, you just try to teleport everything into this code 2, and along the way you detect for errors. And if you detect any error, you just like discard it. Okay. So I should note that there's some like a very nice and very comprehensive prior works based by like Michael Beverland and Alex Kubichin and Chris Zavore, who have actually studied the combination of these two when it comes down to the 3D color code and 2D color code, and argued pretty convincingly that approach would be inferior to the standard magic state distillation. But the key difference here is that you're trying to do like a full-scale error correction, which is scalable, but realistically the threshold that you get is like a super low. But here we're not trying to do anything scalable. We just want to get like any marginal improvement whatsoever. But the upshot is that because we're doing error detection is much easier, maybe we can get something out of it. Okay. So the code that we have in mind is like probably the first thing that you can imagine, which is the 3D color code and the 2D color code. And you can see that this does satisfy the desiderata that I told you about. So here we have something that has a bad threshold, but has a transversal T-gate. Here we have something that has like a pretty respectable threshold these days, but does not have a transversal non-Clifford gate. And it's been known for a very long time that you can actually switch between the two codes by measuring the syndromes in an appropriate way. So at the high level, what we're doing is like something that looks very reasonable. You just prepare the magic state on this like a 3D color code, and then apply some entangling gate and measure, detect for error. If anything bad happens, discard. If not, just accept and see what happens at the end over here. I'm kind of simplifying this a little bit too much because there are actually a lot of details under the rug. So it's not easy to come up with a syndrome extraction circuit that preserves the full distance. So you have to make like a specialized circuits based on flat qubits to ensure that you actually preserve the full distance. That's a lot of work, especially for the 3D thing. And then you have to actually prepare these states reliably, and that is also not easy if you want to just optimize for the logical error rate. So that part was also special. And this transversal gate, you don't want to do it you don't want to do this using, let's say, the lattice search, which would take like too long of a time. You want to do something that is like a quick and something that is quick, like a transversal gate between the two. And long story short, there is such a transversal gate. And so all of these ingredients put together could give us actually something reasonable. So here's the result of the simulation. So depending on what you want to do, you can really consider like two ways of characterizing the fidelity of the magic state that you get at the end of this protocol. One is that you perform the logical state tomography, but when you do the tomography, you do the error correction. So you measure the syndromes, and based on the syndrome outcome, you apply the correction, and then check the logical X, Y, and Z variables, expectation values. The number that you get is like a pretty substantial improvement over the physical error rate, although this is just circuit level simulation. I'm going to tell you about the actual experiment. There's a different way of characterizing the magic state fidelity, which is much more aggressive, which is to when you do the logical measurement at the final step, you discard whenever you detect an error. This is unrealistic in a sense that if we were to use this encoded information later in the computation, this is not exactly what you're going to do. Like imagine like detecting for error when you do when you try to consume this like magic state so that you can apply the T-gate. Imagine you detect any error and just halt the entire computation. Obviously, this is not going to be scalable. That said, this number still has some value, because what you might decide to do is that starting from a small code, you go to a larger code. And along the way, you have a choice of, again, doing a post-selection. Meaning that when you go to larger code, you would still measure the stabilizers of this small code along the way. And you can decide to post-select one more time at that step. What you end up getting when you go to larger code is something in between, and that just depends on a lot of details. Okay, so there's an experiment. Henrik also discussed this. So actually, our work came out with this other group based on continuum, who actually beat us to when it comes down to the fidelity of the magic state. But a long story short, we get something that is actually comfortably below the the error rate of the constituent physical gates. So these numbers, I should emphasize, should be taken with some grain of salt. Here are collected a bunch of numbers spanning from 2024 to 2025. They're all using the same device from continuums like H2-1. But if you look at the papers very closely, you'll see that the physical error rates are not always the same depending on the experiment. Okay? So it's not easy to say which of these fidelities are actually better, because they are just coming from a different physical error rates. That said, well, the bottom line is we get the fidelity of magic state, which is infidelity of magic state, which is well below, certainly definitely below the a 2-qubit gate error rate. And it's actually not that different from the error rate that the logical error rate of the other operations, like the applying logical C0 or the preparing a logical Bell state. So at least at this small scale, it's not clear if a T-gate is really the main bottleneck. Of course, there's a separate question of what will happen if we scale up the system. But as I said before, there's this a growing list of papers that are trying to come up with these very hacky methods for creating magic state on distance 3 or distance 5. And on some of these papers, on the simulation front, they're actually better than us, as of today. So it'd be really interesting to see whether any of these methods work really well in the experiment like we did. And understanding those numbers will be important to understand how we're going to build a large scale a magic state distillation machine. Okay, so to summarize, So we got a magic state, logically encoded magic state with infidelity, which is comfortably below the physical 2-qubit gate error rate. So this is something that I didn't think would have been possible if it was like 3 years ago. Okay? And what's the cost? We use like 26 physical qubits, including all the ancillas, with 83% success probability. So it seems like this is actually like a reasonable thing to do. And extrapolating this further, we can imagine as the magic state becomes sufficiently cheap, we have to think about like how to parallelize. And for that, really thinking about these like catalytic subroutines, I think will be very helpful to like paint the overall holistic picture. Okay, that said, I think there are still a lot of like open questions. One is like how do we actually, like how well does this, do these methods actually work? So one is like how do you actually simulate them? We have some ideas on how to do this for some subset of the protocols, although like this remains as a pretty open question. And there's an interesting work from Margarita and others on like non-abelian codes, and it's just really not obvious like how well this will work because it's just really hard to simulate them. But it'll be good to have an understanding of how this approach of just discarding bad outcomes would apply to this case. Lastly, one thing that has been bugging me for this like a catalytic quantum computation is that the catalyst that I have for the rotation, it is kind of universally applicable to like any of the subroutines that I mentioned, like addition or like a factoring, but they're kind of like inefficient in a sense that if I were to do like addition in constant depths, I'm going to have like lots of these catalyst states like sitting around. So it'd be nice to have some like a more optimized version of these things. Okay, that's it. Thank you.
Thank you, Isaac. Questions, Anthony?
Maybe I missed this, but it seems like you emphasized about the depth, but would sort of picture change if it's just gate counts? Or?
For the rotation, the gate count doesn't change because, well, I mean, at least asymptotically it doesn't change. So let's see. Actually, let me get back to this part. Yeah, so here, let's see. For like an n-bit rotation, I think the Toffoli count is 2n, and in the amortized version, it's almost n. It's not exactly the same as the standard setup in which we count T-gates, but maybe a better way to think about this is that there's like a different way of doing like catalytic rotation with like a log n depths using like a addition. And there, let's see, the T count, well, the Toffoli count is basically n, essentially. So there really isn't a huge difference when it comes down to the count.
Sorry, did you mention that you can reuse the catalyst states?
Reduce?
Like reuse.
Oh, yes.
Could you explain that again?
Yeah, the reason is that you're basically applying a controlled unitary. And, well, the state that you're preparing is an eigenstate of unitary. So it remains unchanged even after you use it.
Right. Oh, okay, I see. Thank you. Thank you.
Yeah, so it's a related question. I guess Gidney, or in some of those papers, they talk about this phase gradient state. Can you just explain why this is better than that? I think it's maybe you've reduced
so like
something.
Right. So there's this phase gradient state, which is like the state that you obtain by never mind. But
it's a particular state, and then you do controlled addition.
Right. So right. So there's a particular state, and you would do the controlled addition on this state to get the phase like this. So So there are like two different limits you would consider. One is when you consider like optimize for the Toffoli count. In that case, okay, ours is like worse by a factor of 2, so it'll make sense to use the other one. The other limit is to optimize for depth. When you do that in this phase gradient state, you would like to get you basically want to do the addition in log depths, which is the best you can do. But we win in the depths. And moreover, when you do this like a log depth circuit, you need like much more ancillas if you just look at the construction. Okay, I guess to apply like controlled rotation, you do need more ancillas here as well. But yeah, so I think in that limit, ours win.
Thanks. Any more questions? So if not, let's thank Isaac again.